What's going on? Everything okay there?
Alrighty, good morning, guys. Can you hear me? So, getting to the end of the semester, and let me talk a little bit about what we are doing today. Let's see if I can get this thing open. Okay, so you should see my screen now. And over here in the Canvas site, you will see a couple of new documents. There is this this file here that's called Shreve chapter 7 and Shreve chapter 8. So we're going to be talking about this chapter 7 today, FX, foreign exchange. And the other thing to note is we're going to be doing some problems today related to foreign exchange. And they are up here in this practice set number 12. So tomorrow you're going to be discussing, there were some issues in homework 8 that TA pointed out, and then this practice set 11 that's down here. Excuse me. And then we'll do some problem practice at 12, and then you'll do the rest of them on next week, next Wednesday. Okay, so grab these two chapters. The plan is to do chapter 7 today, and then chapter 8. Chapter 8 is about Black-Scholes. We'll do that next week. I should also say that while we're here, that if you haven't already signed up, send me an email about when you wish to take the exam. There are only a few slots left on that first Tuesday. Okay. The other practical announcement is about office hours for Thursday. So office hours on Thursday, December, what will be 3rd, they're from 8 to 9 a.m. Oh, now it's mirrored. Is the paper mirrored on your side, or does it look normal on your side? It looks normal. Okay, so I got a new computer, and this is why things are not looking the usual way on my end. I need to figure out how to get it unmirrored on my end, but it's okay. I can look at mirror stuff. Anyway, so on Thursday, December 3rd, we will have office hours from 8 to 9. Friday is going to be the same. Okay. Are there any other questions or comments before we get started on today's lecture? Okay, then let's get started on. So today's lecture is going to be. Today it's about foreign exchange. And this is just called FX. Today's about foreign exchange, and there's an additional chapter 7 on Canvas. This is a PDF file. Okay, so the new feature is this object. It's to note about Q, n going from 0 to say, infinity. This is an exchange rate. Right, so that's a new thing. This is a stochastic process. And it could be, so as an example, it could be a traditional binomial model where, say, Q0 is equal to 2, and then it can go up and down as we worked with so many times in this semester. So it can go up to 3, and it can go down to say 4/3, and then it can go up and down. It can go up to 9/2. It can go down to 2. It can go up and it can go down. So this here is the values. This is Q1 of head. This one here is Q1 of tails. This one here is Q2 of head. This one here is Q2 of head tails, which is also the same thing as Q2 of tails heads, which is equal to 2. And this one here is Q2 of tails. Okay, so that's the new object. This is something we have not had before, and so let's talk about what it does. It's a stochastic process, but what does it do? Well, it's the exchange rate. So as an example, if you say that this means dollars, and I'll call that for domestic currency, and then we have pounds, this is foreign currency. So the way that it goes is that you convert pounds to dollars using this process Qn. And the way that we're going to do it is by multiplying with Q. Right, so if X is a dollar amount, if X is a pound amount, well then X times Qn is a dollar amount. Right? If, for example, if you look at x to be 1, so you're looking at 1 pound. This is then equal to QN dollars. So you take, so 1 pound is equal to so if you have x is equal to 1, then how much is 1 pound worth in dollars? That will be that 1 times QN with 1 times QN dollars. So you take whatever amount you have in pounds. If you want to get the corresponding amount in dollars, the way that you do it is you multiply onto the QN process. And now, so you can go the opposite way. You convert from dollars to pounds by dividing. Does that make sense? We're good on how we move from pounds to dollars. We multiply whatever pound amount we have with the exchange rate, which we denote by QN at time in. So now we're going to do derivative pricing in a model where we have both foreign and domestic assets. So what are our assets? We're going to have domestic. Okay, so domestic, this is the dollar. We have a domestic bank. So this is what we've been writing as S0n plus 1 is equal to S0n times 1 plus R. But this here is how the textbook, I don't know why, but he changed it. So he started writing mn plus 1. He writes this as mn times 1 plus R. This is the textbook's notation. R here, this is the interest rate, as usual. So there's a domestic bank, and then there's a foreign bank. So that's the pound. And the way that we would write that would be S0, and then we would put maybe an F here for foreign. And then we would write this as N0F 1 plus R. But the way that the textbook writes it is as mn plus 1 and puts an F. This is equal to mnf times 1 plus RF. So again, this is This is the textbook's notation. But so this one here is denominated in dollars. This is denominated. This is denominated in dollars. And this one over here, this is denominated, say, in pounds. So we are interested in, right, so there's no randomness here. These are constants. So both R and RF, these are constants. So there's no randomness in either M or MF. So the randomness is coming in. The randomness is coming in through the exchange rate process, because here, this is where we see the coin flips. So we are interested in the, so we define, so we convert the foreign bank into dollars. So the way that we do that is by introducing the asset, which we're going to call SN. So SN is defined as, we take the price, so this is M, if we follow the textbook's notation, MF times Q. Right, so this is in dollars, this is denominated. We took the foreign account, the foreign bank account, and converted that price into dollars. So now this is risky. So this here has randomness. Right, because Q, even though MF is not random, Q is random, right? So we have now randomness in SN. And this is because Qn is random. So an investor, he can trade in M and in S. So we want to see if there's no arbitrage. Our model is going to be that our Qn plus 1, this is equal to Qn times the coin flips. So this will be my psi n plus 1. These psi is the IID. And the coin flips. So you go up to U, he calls it UQ and DQ. So then what I can do is I can plug it into this formula here. And so I'll get that Sn plus 1 is equal to, we'll use the formula, it will be Mn plus 1 F times Q n plus 1. And then we'll work out what this is. This was the foreign money market account.
Shut it off.
Can you okay, mommy? So the foreign bank account, we can plug in this expression here first. This is M n f times 1 plus rf. And then we can plug in what q is. This was q times the conflip. So we now realize we're going to get the same structure that we're familiar with. We will have Sn here, and we will Sn plus 1 here, and we'll have Sn on the right-hand side. This will be my Sn, and then I'll have 1 plus Rf times the conflip. So this is quite close to the model. This is similar to our usual stock price. The only difference is that my conflips here are going to be taking values uq and dq. So you can see that if we look at u, the up factor to be uq times this 1 plus rf, and I look at the down factor to be dq times 1 plus rf, this is exactly what we're used to. And in particular, if you want to have no arbitrage, then we know that there's a relationship between ud and r, and the relationship was, how was it? So we would have, this would be my u, this would be my d, and then I had to have 1 plus r in here. So I need to have d less than 1 plus r less than u, and then plug it in. And then we plug it in, we're going to get dq 1 plus rf less than 1 plus r less than u. So this is uq 1 plus rf. And we can then divide over. We're going to get that dq must be less than 1 plus r divided by 1 plus rf must be less than uq. Any questions so far? Any questions so far, guys? So now we have the no arbitrage condition. Then we can do the risk neutral probabilities. We want the expectation under the tilde measure of Sn plus 1 divided by we want the martingale property of the discounted stock price. So we wanted this to be Sn divided by Sn0. So let's work out what the left-hand side is. And again, this quantity here, this is what the textbook is calling M n. And this here is what it calls Mn plus 1. This is just textbook notation. Okay, so we can plug in what the left-hand side is. What do we get? you'll get here, this is 1 over 1 plus r. And then we have the expectation of Sn plus 1. Okay, that was the one we just had. That was the one we had up here. Sn plus 1, this was Sn times 1 plus Rf times the coin flip. So I want this to be Sn. And we can cancel out the s's. We can compute what the expectation is. I get 1 plus Rf divided by 1 plus R times this was UQ P tilde plus DQ 1 minus P tilde. I want that to be 1. And of course, we want P tilde to be somewhere between 0 and 1. Okay, so this is going to give me P tilde. And that's going to be, of course, the same as what we used to, right? P tilde is going to be 1 plus R minus D divided by U minus D. And then you just insert what D and U are, namely these two factors we have up here. Of course, we can play the same game in the foreign world. So there's a similar argument in the foreign. So this was this L, the pounds, in the foreign currency. Right, so here we need to convert MN to pounds by dividing. So we will have our SN, but now in the foreign world, this would be M, the domestic bank account, divided by the exchange rate. So if we do that, we will see if we can obtain more or less the same relations as before. We will be able to write here. We need to write Sn plus 1 F. How would that be? Well, it will be quite similar to M. So it will be Mn plus 1 divided by Qn plus 1. So it's a domestic bank account denominated in pounds. That will be Mn times 1 plus R. And then we would divide here by Qn times the coin flip. So this would be, the first part will be SNF times, and then 1 plus R divided by the coin flip. So now we can define the up and down factors. We will then have UF. We have UF would be 1 plus R divided by yeah, so it's a good question which one we should have. We'll probably have DQ here. Yeah, we should have DQ here because this is going to be smaller than the other one, so this is going to be the L factor, and we're going to have D df would be 1 plus r divided by q q. And then again, we want to find, then you want to find with neutral probabilities such that you have the martingale property. You want to find with neutral foreign probabilities. And so we want to have this object up here is in f divided by the foreign money market account. So that would be what we would usually write as that. But again, the textbook insists on writing this here as M and F. We want this thing here to be a martingale under these P tilde F. One could also ask, and the textbook spends quite a bit of pages on relating these two meshes. So let me show you how one can do this. So there's a relation between them. Whenever I want to relate two meshes, what should I probably use? Whenever I want to relate two meshes, what is the object that I should study? What takes me from one measure to another measure? That's right, Schumik. We should always use Radon-Nikodym derivatives, right? So let's just recall a little bit about that. So this is just a note. Recall that, let me use some different symbols here. Let me recall that if I have Q, let me say Q is equivalent to P, if I can find the Radon-Nikodym derivative, dq dp is strictly positive, and it has expectation 1, and so I have a random variable, has these properties, and I can compute probabilities, Q probabilities, by integrating this Radon-Nikodym derivative. And I can do this for any set A and my sigma algebra. We also sometimes look at the Radon-Nikodym derivative process. And the Radon-Nikodym derivative process, so this is denoted by Zn. It has this property that, well, it's a martingale So Cn is positive, starts out at 1. Cn is a martingale, and what? And if I look at Q on a set A, I can write that as an integral of Zn dp for any set A, not in F, but for any set A in F. So this was just a little reminder of some of the theories that we talked about before, and one of the key there are many properties of this radical derivative, but one of them is coming out from Bayes' rule. So Bayes' rule says that let's say Yn is a Q martingale if and only if, and then this radical derivative process comes into play if and only if Yn times Zn is a P martingale. And maybe we should just, because we've been using this and we'll be using it now again, let's just keep the proof in mind. For example, if I want to go downstairs, so let's go downstairs. So then you know, so you have that the conditional expectation under Q of Yn plus 1 given Fn, you know that this is true. And so Bayes' rule comes into play, because what Bayes' rule says is that the left-hand side, and so this one here is Bayes. This one here is Bayes. He says, well, the way to compute this is replacing Q up there by P, and multiply onto the radical derivative. You need, this one here is going to be Fn plus 1 measurable, so you need the Zn plus 1 here. And then you need to divide by the conditional expectation of Zn plus 1 given Fn, and that's going to be Zn. Right, so now we move this thing to the other side, and you get that you have the P martingale property. Okay, so this is coming straight from Bayes' rule, that you have this relationship between P and Q martingale. So if you know what the radical derivative process is. So whenever we have measures, knowing what the radical derivative is probably going to be the key to solve the problem that you're facing. So now this was just a little refresher, right? This is something we talked about in the past, and now we have two martingales. We have a martingale. We have a martingale under P tilde. That's going to be S divided by the bank account in the domestic currency, and then we have foreign set of risk neutral probability. So that means that the domestic bank account denominated in foreign currency divided by the foreign bank account is a martingale. So these two things should be related to each other. And so what's the radical derivative? Right, so let's apply this to the martingales. So what was the first one? This was, so if I took Sn divided by MN. So SN was the foreign bank denominated in US dollars divided by the US bank account. We know that this is a P tilde martingale. And then we had the other one. This was SNF divided by MNF. And what was this one? Well, we go back and check. Go back and check. SNF divided by this guy. So what was what was SFN? This was MN divided by QN. Right, so this is the domestic bank account denominated in pounds. So this is the US bank account denominated in pounds. This is MN divided by Q. That was the first part, and then we need to divide by MNF. So we know that this is a P tilde F martingale. So what's the Van-Nicolum derivative process? So what are we claiming? We claim that Cn is equal to Sn divided by Mn divided by Q0. So we claim this is true, so we need to check. Just some sanity checks. So we have that Cn is positive, right? So it's the it's a positive process. Yeah, so this is positive. We should also check that it's Z0 is equal to 1, and that's why we divide it by Q0. Right, this is equal to S0 divided by Q0. This is equal to 1. And it's a martingale. Well, we know it's a martingale because this is a constant. Sn divided by Mn. That's the one we have over here. This is a P martingale. And it's a martingale. So then the remaining question is, do we have that? Do we have this thing that we can move between these martingale structures? So we're saying that SNF divided by MNF, this is a P tilde F martingale. That was what we're saying down here at the bottom. And then we use base. So base says that, well, this is the same thing as Zn times that ratio. So this is a P tilde martingale. And so is that true? Well, let's work out what this quantity here is. What does it become? So on one hand, I have this is the claim that Zn is equal to Sn divided by MnQ0 times this ratio. So we need the SF. What was SF? So over here it was M divided by Q. M divided by Q. And then we had, that was my SF. So we also need to divide by the MF. Okay, so some things are canceling out here. We're seeing that the M's cancel out. And then you have your Sn here. Remember what he was equal to. Running out of colors. So this here was equal to, S was equal to the foreign bank times the exchange rate divided by Q0 times 1 over Qn, M, and F. And now we see everything cancels out. I end up with 1 over Q0. And this is indeed, which is a constant. And it's a piece of the material. So this was just a little bit about the model setup. You can look at it from either a dollar point of view, or you can look at the domestic point of view, or you can look at it from the pound point of view, from the foreign currencies point of view. Either one is good. You can, yeah, either one. I mean, they're all equivalent. So whether you started in one or in the other, this is all the same. And depending on the problem, one might be easier than the other. What we're going to be doing now is looking at start doing some examples on what kind of derivatives one will be interested in such a setting as this one here. The first one is we're looking at exchange rates. So the first derivative we're going to be looking at is a forward, which is similar to what we've been discussing in the previous lectures, where we had forwards in a stochastic interest rate environment. So here we don't have a stochastic interest rate environment. We have a stochastic exchange rate environment. We can still talk about forwards. And so we're going to start doing derivatives. And the first one is a forward. This is a forward foreign exchange rates. So the picture is, timeline is as follows. We will have two time points. We'll have N, we'll have M, we'll have 0. And so here at time M, there's going to be £1 pound exchanged. So one pound, which is equal to QM dollars. So at time, so the mechanics is that at time N, you exchange 1 pound for, let's use the notation in the book, FOR and then NM. So this here is going to be, this is going to be measurable with respect to time N, dollars, where this one here is FN measurable. Right, so the payoff at M is you're going to get the $1, which is the same as Q. You're going to get Q M minus the forward So this thing here, this is if M measurable, right? And this one here is, this is if N measurable, and M is bigger than N. And in particular, if you're sitting at time 0, right, so the picture is you have N is smallest, M is biggest. So in particular, if you're sitting at time 0, you have the exchange rate. So you're going to get £1. This is worth QM dollars, and you're going to be paying a constant for it. So in this case, this here is now going to be constant. So what is this fair forward rate? So what's the fair forward? You need to evaluate. We find this forward rate by solving 0 is equal to the value. We figure out what is the price. This is the payoff at time M. We roll the payoff back to time little n, and we equate the price to 0. So this will be E tilde n of this payoff. And we have to discount it. So we're going to discount it. This is something we get at time M. If we discount it back to time 0, we do that by dividing by M. And then we roll it forward. If this was back to time 0, we have to only get it back to time little n, so we roll it forward. But in our model, the interest rate R is constant. So these quantities here, they are not random. So we can pull them outside the expectation, divide over, and we'll see that this is equal to 0 if and only if the forward rate is equal to the conditional expectation of the future exchange rate. So this here is a martingale. This here is a P tilde martingale. This is a Levy martingale. Conditional expectation of a random variable is going to give us a martingale. And we can actually work out what this thing here is. So we can compute this conditional expectation here. So it's going to be a martingale. We can compute what it is. Okay, so to compute this forward rate, we'll use that. What is the defining property of the tilde probabilities? Well, it is that Sn divided by Mn is a martingale. And so what was this? The security was the foreign bank denominated in dollars. So that's what we have here, divided by Mn. And we can plug in what these two are. This will be 1 plus R f to the nth divided by 1 plus R to the nth times Qn. Right, so I know that this is a martingale. So if I want to compute what I have up here, we can write we can write this forward rate on the exchange rate as a conditional expectation of QM. So I want to be able to compute what this is. Well, the way I'll do it is I'll use that this object here is a martingale. I'll use that this object is a martingale. So if I move this coefficient here inside, I'll get a martingale. Okay, so then if I want to make it true, I also have to have it outside. So what we have is, I want to put something inside. What I want to have inside is 1 plus R F divided by 1 plus R. And then my Qn, because this is my martingale. But then I need to correct it with this coefficient here. Multiply by the inverse. This is 1 plus R divided by 1 plus RF to the end. And now I can use the martingale property of this product, the one we just had up here. So I'll use this quantity here. This is what goes in to this equality sign. I'll get 1 plus R divided by 1 plus RF to the nth. And then this thing here is where I use the martingale property. Instead of M, I can put in an N. 1 plus R. Something wrong here. This should be an M here. I need the inverse of what I have here, so this should be an M. And then I'll have 1 plus RF divided by 1 plus R to the nth times Qn. So that's my forward rate. Any questions on this?
Hello. Why there? Why the 1 add RF divided by 1 add R? No, the next line. The last line, the right side. Why the right side? Why there? Yes, why there is a N? Why N?
Because you have a martingale, right? And you condition. Right. So what do we use? So if let me call it Yn. If Yn is a martingale, then the conditional expectation of Ym, so here m is bigger than n, this is Yn.
Okay.
Right, because the way that you do that is you write the left-hand side, you can write this as the conditional expectation of the conditional expectation of, say, minus 1 of Ym.
Okay.
Right, and now the inner guy here, this is iterated expectations.
Okay. Okay.
And so now this quantity here, this is the martingale, this is Ym.
Okay.
Martingale. So then you see, you can go one back by saying, so apparently you have that Yn is equal to the conditional expectation of Ym minus 1. And then you can keep going back all the way to, if you're worried about, if your worry was that the martingale property says that this is the martingale property. But then you can iterate forward, because you can say that, well, this guy is the same thing as the conditional expectation of yn plus 2 given if n plus 1. And so then you use iterated expectations like we did here, combine them, and then you'll be able to write this here. It's the same thing as the conditional expectation of yn plus 2 given if n. This is going to be yn. And then you just keep doing this until you get up to m. Was that your question?
Yes, thank you.
Right, so here we have a martingale. So what we have to compute was not quite what the martingale is, but fortunately the difference is something deterministic, like non-random. So I can move this quantity in and outside the expectation with no problem. And so I can write this thing in terms of that martingale structure. And so here I'm having an m is bigger than m is bigger than n. And so for that part here, I'll use the martingale property. This one here, I'm just leaving the same. So this gives us an expression for the forward foreign exchange rate in terms of the exchange rate. There's this correction term. Other questions, comments? So let me do one more thing here with this example here before we move into some other problems. The textbook has a section in here where he writes about replication. And this is section 7.5. He talks about replication. So let me let me specialize to the case. Let me specialize to the case where the picture is you have your the payoff is happening here at time capital N, and we're sitting at time 0. So let me specialize to the case. So here we're going to get this payoff. This is my Qn, right? And we're paying the forward rate for it. So this is my forward 0n. Right, so again, this one here is a constant. And this one here, this is the exchange rate. At n, right, so this is random. So replication, so at time 0, you enter a forward contract. This has no cost. Right, and so then you hold on to it, and then at the end, you get the payoff. Qn minus this forward rate. So it costs nothing to enter, and then at the end, you get this payoff, and this could be both. This could be positive or negative, depending on Qn. So what this section here is about is how to replicate this payoff. How do you set up the replicating portfolio? So what's the replicating portfolio? So what's the replicating portfolio? Right, so we want to buy delta. This is the number of S. What was it? S was, this was the foreign money market account denominated in dollars. And of course, we can also invest in the domestic bank account. Right, so how do we trade in these two securities, the foreign bank account denominated in dollars, and how do we trade in the dollar bank account to replicate this payoff? And that's something we've done. This is something we've done a number of times in standard, like an equity setting. So let's try to do it just one more time in this setting where you have the foreign exchange rates. So the way that we go about it is we need to roll back the payoff, computer conditional expectation. So let's try to do that. We need to compute a conditional expectation. We need to roll this payoff. We need to roll this payoff back to say time n. So we have the payoff that comes out here in the future. This is the payoff. We need to be able to roll it back in time, so we can roll it back to n-1, n-2, and so on, and all the way back to time 0. And the way we do it, we compute a conditional expectation. So we need to compute, this is back, roll back to time n. We roll it back to earlier time points. So we need to compute a conditional expectation. Then take the payoff. So that was the payoff, and we roll it back to time little n. Okay, so we start by rolling it back all the way to time 0. So that would be m n, and then we roll it back to time, roll it forward to time little n. And this calculation here is quite similar to what we just did. Let me break it up into 2 parts, right? There's a random component here. This is not random, so we can break the expectation into 2 parts. Okay. So the first part will be 1 plus r to the nth divided by 1 plus r to the capital N, and then the conditional expectation of Qn minus, and then the same 1 plus r to the nth divided by 1 plus r to the capital N, and then this forward 0n. So let's work out what these various quantities are. Well, the middle guy we know what is, because we just computed him on a previous slide. Let's just copy paste from that previous slide. Just make sure I get it right. So the first one is this conditional expectation of Qn. Well, that was the one we had here. That's where we used the martingale property and we figured out what this was. It's this long mess over here. So let me paste that in here. This is 1 plus r divided by 1 plus rf to the power n. This one here was 1 plus rf divided by 1 plus r to the power n times Qn. And then the forward rate, we also had an expression for. It was this thing here, but for n equal to 0. So we get 1 plus r divided by 1 plus r to the power, this will be an n. Little n is equal to 0, so we're going to get q0 here. And now hopefully it will simplify a bit. See how much it simplifies. See, you have, there's something down here and something up there. So cancel that out. That's going to be gone, and that's going to be gone. You have 1 plus r in here divided by it here, so that's going to be gone. So we left here with 1 plus r f to the power n divided by 1 plus r f to the power capital N times qn. On the other side, we have a minus, and we see here 1 plus r. It's downstairs here and it's upstairs here, so that will cancel out. And we're left with 1 plus r to the nth divided by 1 plus r f to the capital N times q0. So that was a conditional expectation. We then have to set up the replicating portfolio. We use the formula. So we just make another note here. We call the formula delta n is equal to, what was it? It's like Vn plus 1 in the upstate minus Vn plus 1 in the downstate, divided by, and then it'll be Sn plus 1 in the upstate minus Sn plus 1 in the downstate. We've had those formulas in the past. We do these by setting up the replicating equations and solving them. And so we use this formula now because we know this here is my Vn. So let's figure out what the various quantities are. Vn plus 1 in the upstate. Everywhere where you see n, you have to put in n plus 1. So we get 1 plus r if n plus 1 divided by 1 plus r f to the nth. Then you have your q, and your qn plus 1, this was equal to qn times u in the upstate. And the other one, there's nothing random about him, so it's just replacing n with n plus 1. Right, so here we're using that qn plus 1 is equal to qn times the psi n plus 1. That's what we're getting here in the upstate. We also need to work it out what it is in the downstate. So we replace little n with little n plus 2, 1 plus r f. We replace little n with little n plus 1. So we have here qn plus 1, this will be qn times dq, and then the same quantity. So those were the this is what was upstairs in our ratio, and we need what's downstairs in our ratio. So the risk of securities value in the upstate and the risk of securities values in the downstate. Well, first we call that SN plus 1. This was the foreign bank account. It was MN plus 1 in the foreign bank account times the exchange rate, QN plus 1. So this here is equal to 1 plus RF to the power n plus 1. And then Q, we'll use the formula up here. This would be QN times psi n plus 1. So to figure out what's downstairs, we will write Sn plus 1 in the upstate. It will be this quantity here. And then Qn. And then it will be a U, Q. And likewise in the downstate, use the formula 1 plus RF n plus 1 Qn dq. Take these 1, 2, 3, 4 expressions and you feed them into the formula. And we only get a long mess now. So insert into the star to get what? Well, we need to take the difference of these two. Okay, so the constant coefficients, they don't matter. So they will drop out. We're going to be dividing everywhere with there's a Qn here, Qn here, Qn here, and Qn here. So all these Qn's are going to disappear. Okay, so let's start by doing that. Delta n is equal to, and then it'll be this long mess. It'll be downstairs, it will be 1 plus RF to the n plus 1, and then the differences in the UQ minus DQ. And then upstairs it'll be, the Q's are gone. These terms here, they don't matter because they're going to get subtracted from each other. So we'll write here, UQ times UQ, then it's the same factors. It'll be UQ minus DQ times what would be 1 plus RF to the n plus 1 divided by 1 plus RF to the nth. What are we going to get here? These will cancel. And this term here will cancel that term. We're going to be left here with 1 plus 1 divided by 1 plus RF to the nth. So long calculation. This is how you invest in the foreign bank account. And what you can see is this quantity on the right hand side, this is there's no n. There's no n. So it is a buy and hold strategy. You buy this many, because there's no little n on the right hand side, this doesn't change with time. Any questions on the example we did? Okay, so what we did was we introduced foreign exchange, right? So the new thing there is is the exchange rate. How do you convert, say, pounds into dollars? And we did an example where you write a contract type, so forward foreign exchange rates. So forward foreign exchange rate, it gives you the right to buy a 1 pound, say, at a future time for a fixed price. Okay, so what is that fixed price? Well, that was the first thing we figured out. But of course, when you're talking about pricing, you should also have the replicating portfolio somewhere. And so that's what we spent the last pages deriving. And it turns out that in this particular model, the replicating portfolio for the forward is a buy and hold strategy. You just buy a certain amount of the foreign bank, right? Delta N, keep in mind what it was. Delta N is the number of units of the foreign bank that you're holding. And that turns out to be a constant. It doesn't change with time. So it's a buy and hold strategy. Are there any questions or comments? If there are no questions or comments, then I propose we take a little break, switch over to the other Zoom link, and oh, there was a question. The next Thursday office hours, I believe so, unless something comes up. I mean, I'm only talking about the office hours. I'm only talking about the office hours on December 3rd, right? So the office hours on Friday, they're going to be the same. And next week, unless something comes up on my end, it's going to be the same as what it usually is. It's just something has come up on Thursday. I can't make it work at the later time, so I moved them earlier. Okay, let's take a little break and then get back together in a little bit.